Okay. Hey, Google, change the light color to white. Why is it still going? Screen, start the broadcast. Okay. Okay, optimize. I'm gonna hop over here, change the view to single page. All right. All right, greetings, scholars. So I hope everyone is doing well. Hope everyone had a great weekend. Let me see, as far as announcements, so we're in the home stretch. I'm under the impression that we have like 3 sections remaining, right? 4.4, 4.5, and 4.6. So my intent today is to work on section 4.4. We're pretty much done. We're pretty much done. So I know I emailed a few students that had like maybe 4 or more unexcused absences. So if you're in the email thread, you need to respond, because I'm more than likely going to submit those names. If I don't hear from you by like Thursday or whatever the email said, then I would submit your names. Or if you think that you have 4 or more unexcused absences, just kind of contact me at the end of class, like, hey, please don't purge me. I intend to finish, yada, 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 right? I'm just trying to kind of get to those students that are no show, no call, that I haven't seen in an excessive amount of time. There's some other special cases, but though we've already kind of like gone back and forth. So, yeah, but so that really doesn't apply to most of you all that are here. I'm just saying, but if you think you might be in that boat, or if you know somebody in the boat, then they just need to speak up, right? That's all that really needs to happen. If you just let me know your intent, do you intend to finish, or would you like to be removed, right? Okay. And it's such a travesty because like to come so far, like we've come so far, right? We're 4 chapters, this thing is what it is. It's a challenge. I'm not gonna lie. Like I know it's challenging. So it's like, but but to come this far, you didn't come this far to come this far. You came this far to go further, right? So anywho, okay. Let's just kind of go ahead and get into today's material. I think I would like to do my podium. That's fine. Okay, so continuing on chapter 4, integration. The main concept behind integration is that it's the reverse of the derivative of differentiation, all right? So given a function, the first 3 chapters, we've been exploring what is a derivative, how to find a derivative, applications of the derivative. So then with chapter 4 is the reverse of differentiation. So given a derivative, how do you work backwards, right? And we've explored like, in a graphical sense, what does the integral tell us? The antiderivative, what does the integral tell us? And in a graphical sense, that's essentially the area under the curve, right? So we're just going to kind of continue that narrative. And so today we'll be looking at section 4.4, properties of definite integrals, additive property, average value, and moving averages. Okay, let's take a look at this. So a few objectives here. 1, use the properties of definite integrals to find the area between curves, solve applied problems involving definite integrals, determine the average value of a function, and find the moving average of a function. Okay. Let me see. So for A strictly less than B, strictly less than C, notice that B is between A and C. So the integral from A to B of a function is going to be the same as the integral as x goes from A to, sorry, let me back up. The integral from A to C of a function is going to be the same as the integral as x goes from A to B of that function, plus the integral as x goes from B to C of that function, right? So I think last time we said that the integral is the area under the curve. Notice we have a B between B and C. So you can kind of essentially break apart the integral if you have some intermediate B as seen in this image, right? So you can break it up into multiple integrals. For any number B between A and C, the integral from A to C is going to be the integral from A to B plus the integral from B to C. Okay, not too terribly bad. So find the area, find the area under the graph of this function as x goes from -4 to 5, right? And it's basically a piecewise function. So we're given this image and we want the area. So we can break it apart into its simple shapes. Let me see. What is that, a rhombus? What is that one? That one's x squared, okay? So, okay, I think let's sit down for this one. Being a little bit indecisive again. see. So if we want the area under the curve, what we can do, so we'll say the integral as x goes from -4 to what, 3 of f of x dx. I'll go ahead and kind of do my substitutions or do my plug-in or whatever. So from -4 to 3, that function is what, 9 dx, plus the integral as x goes from 3 to 5. Of x squared dx, right? So we basically broke the piecewise function up into 2 parts. Find the integral, the definite integral between those bounds, all right? So the integral of 9 is what, 9x, right? Because the derivative of 9x is just 9. We want to evaluate that function as x goes from -4 to 3, plus the integral of x squared is going to be what? X cubed over 3. So that's going to be x cubed over 3 as x goes from 3 to 5. Okay. So then this is going to be 27. Let me see, it should be minus, but then 9 times -4 is what, 36? So that's going to become what, plus 36? Because you say the upper bound minus the lower, but double negative becomes positive. All right. So we said the upper minus the lower. Then we're going to say plus when x is 5, so that's 125 over 3, minus 27 over 3, which is what, 9? Yeah, minus 9. 9 over 1 is 27 over, I'm going to leave it as 27 over 3 for now, just because it has the same denominator. Okay. Let me see, 100, so 98, 16, 17, 98 over 3. Let's just use my calculator. Reload and refresh. So it's like we've done updates to this thing. Okay. Let me kind of check my work. I know that's 27 and that's 36. Double negative is positive. 125. Okay, so we'll do 27 plus 36 plus 125 over 3 plus minus 27 over 3. 2/3, so 95 and 2/3. My dog has been chill all this time. Now when I started teaching, she want to start pacing. For whatever reason, she started pacing, it makes me so anxious. Like, cause it's so subtle, but it's just like, well, I was like, cause I'll be sitting there, I was like, why do I feel anxious? And then I realized my dog is like walking circles around the room. I'm like, oh my God. Can you lay down? Lay down. Thank you. Okay, so we got 95 and 2/3. Let's see, how do we do? 95 and 2/3. I feel like I should pause for the cause. You know, if there are any questions, just feel free to unmute yourself or type in the chat. Matter of fact, let me log in here. Let's go to Zoom. Join. Don't connect. Blah, blah, blah. That's correct. Join. Say as a participant. Okay, you guys, I guess we're okay for now. Let me check here. Yeah, you guys look okay. I ain't gonna worry about it. All right. We got the same thing, so let's move on. So quick checks I usually leave as an exercise for you all. Okay. So we have this theorem 6. So it says, let f and g be continuous functions, and suppose that f of x is greater than or equal to g of x over a closed interval a, b. then the area of the region between the two curves as x goes from a to b is going to be the integral as x goes from a to b of f of x minus g of x dx, right? So I think the main takeaway here is that f of x needs to be greater than or equal to g of x, essentially above, right? Above g of x. And then if you want the area of the curve between the two regions, you say the integral is x goes from a to b of f of x minus g of x dx. Okay. You don't want to work? Okay. Let's try you. There you go. Okay, so find the area of the region that is bound by the graphs of this. First, look at the graph of the two functions. I am going to create a little bit of space for myself. Let me see what I can do. Let's do something like this. I want to copy and paste. And I just want some blank space. All of that. What I'll do is crop a bit. That's good. No. Okay, that's fine. Find the area of the region that is bound by the graphs. So as x goes from where? 0 to 2, notice that f of x is above g of x for that interval. So if we want to find the area of the shaded region A, that golden region A, we would say what the integral as x goes from 0 to 2, f of x is essentially f of x minus g of x. So I'm going to capture that as this 2x plus 1. Now, if we say minus g of x, we do need to be aware we need to distribute a negative there. All right, I'm kind of skipping a little bit of steps in the interest of space. So just keep in mind I'm distributing a negative into this g of x. Right? It probably would have been a little bit better if I wrote it as f of x minus g of x dx. But yeah. All right, so this is essentially what we're integrating. The main thing is just be aware to distribute the negative into the g of x. Okay. So then from here, we could even simplify it a little bit first. Like those ones, like they're going to cancel out. So like this is going to cancel that. And then we can just take the integral. For instance, the integral of 2x should be what? X squared. As x goes from 0 to 2. Well, actually, we don't have to do the individual. I don't know why I'm breaking it apart like that. Okay. And then what x squared becomes x cubed over 3. Okay. And we want to evaluate this antiderivative as x goes from 0 to 2. So we plug in 2, we get an answer, minus when we plug in 0. Now, right off the rip, if we plug in 0, it looks like that whole thing collapses to 0. So it looks like the final result is just going to be when we plug in x equals 2. So when we plug in 2, that's going to be a 4 minus, what, 8 over 3? I'm going to go ahead and rewrite this guy. So if that's 4 over 1, that's 12 over 3. It's like it's 4 over 3 ultimately. Okay. Let's see, how do we do? 4/3. Points of intersection. Did we miss something? 4/3. Okay, yeah, we're good. Okay, let's keep going. All right, this is example 3. So a clever college student developed an engine that is believed to meet all state standards for emission control. Pause. Just a random story. Have you all heard of like in somewhere in Africa? I don't know if it's Nigeria or Ghana or someplace like that, but I think it might be Nigeria, but I'm not sure. Don't quote me on that. But there's a guy that discovered how to convert radio waves into energy. So basically, he's built all these devices that like basically free energy devices. So like cars, what else? Just appliances, like, you just turn it on, you know. And so, part of the story was like, when he figured it out, he had scheduled to like meet with some people here in the States. And obviously they tried to kill him. And he said that like when he was coming, they were poisoned. He said that his friend was killed, and he said he just made it out by the good grace of God. Like he just barely made it out. And so I mean, like I remember the first thing that he showcased was like a self-powered TV. And his claim again was that he can take the radio waves and the signals that we're inundated by, that are just always there, and convert them into electricity. But honestly, if you want to take it a step further, I've seen things where people, and again, I just need to kind of take some time to confirm or deny some of these leads. I've seen things where people would take like, kind of like Benjamin Franklin, where they would take a drone with a wire up into on a sunny day, just up into the sky. I don't know, two or 300 feet off the ground with the drone, and he did an experiment. I can show you the video, and it's something simple. You can just confirm. You can do your own test to confirm or deny. But he was like, yeah, he was able to basically siphon electricity right out of the sky. So for free energy. And so it seems almost like, this America is infamous for tricking us or bamboozling us into paying for things that are free. So this is why I actually study mathematics, because I researched this stuff, and I was like, okay, I do intend to like do experiments and see, okay, can I replicate the results, or is this just fake? Yeah, because again, you don't really know until you start questioning for yourself, until you start doing your own research, your own experimentation. Can you replicate the results? Can you confirm or deny their claim? Right? Because if you just take at face value what an authority tells you, they'll tell you anything. They'll lie to you, even to your own detriment, even to your own demise. They don't care. They're just gonna shrug it off, make up some excuse, throw money around, and keep moving. So until you take that time to like think critically for yourself, question authority and stuff like that, we're just gonna be like lambs to the slaughter. Right. So I know this stuff is like, it's a little bit disconnected from what we do, but this is why I study this stuff, like math. It's how to think critically, how to like, okay, how to problem solve, and like, okay, is this true or is this fake? Essentially, I'm a truth seeker. So, and it's so funny because a lot of the evidence that I get, the conclusions, I was like, okay, if this is true, this is really wild and trippy. A lot of times, truth is stranger than fiction. And then it's like, you got to be careful about talking to people, because they'll look at you with the side eye. But then, what inevitably, what always happens, it always comes to this point where they come like, well, dang, Charles was right. I mean, that's been my entire life. Like when I try to alert people to stuff, they look at me with the side eye, and I throw it up. So now at this stage in my life, I'll say it once to people, and then I'll release it, because I realize that the truth cannot be told; it can only be realized. If I sit there and go toe to toe and eat battle of ego wills, trying to beat a dead horse about what's true or not, it's just a psychic battle, and it's just a battle of ego wills. So at this stage, I'll say it once. I feel like my job is to at least alert people, plant the seed, and then you got to give it time to germinate. You got to give them time to arrive to their own conclusion. Again, the truth cannot be told; it can only be realized. So interesting things, right, about this whole free energy, and don't get me started on Tartaria and all this other stuff. Like it's some really, really interesting stuff. So anyway, but yeah, so apparently, and his name is like Maximus or something like that, the guy in Africa that supposedly are building these free energy devices. And like in the comments, they're like, protect this man at all costs, because every time somebody creates an invention that would move us forward, these big oil companies, these big companies, they assassinate. Because if you're in power, you're not going to allow your subordinates to have power. You're going to do everything in your power to suppress information so you can maintain power. It makes sense. I'm not saying it's ethical or it's right, but if I didn't care about the lives of other people and I wanted to control them, or at least try to control them, then I could see why somebody would do that, especially if you don't have if you don't have a soul. If you don't care about what happens to another being, then so be it. But so anyway, don't get me started on all that. So just interesting things. So back to this. So a clever college student developed an engine that is believed to meet all state standards for emission control. The new engine's rate of emission is given by this, because the other guy I wanted to mention, there was a white guy. He built the water powered car, right? A car that he built a car, he drove across country on like a gallon of water. You got to cross country and back. You know, even right now, you can build a hydrolysis device where basically it's like electric plates. You put a charge in it, a low charge, some kind of charge. If you construct it right, you can separate the hydrogen from oxygen, and then you can, and it'll come off as like gas, like that you can burn. So instead of burning like using propane or things like that, you can actually just take water, separate it, and you can have fuel, like for burning, cooking, heating, power, stuff like that, just off of water. So like these are the kind of things that honestly, if I weren't working, this is what I would be studying. So like that's when I know I was like, okay, why are we so inundated with distractions? Because they want us chasing our tail because they don't want us to realize this kind of stuff. If we were sitting at home and left our own devices, like if there's another guy, Nature Jab on YouTube. I don't know if you ever heard of him. He and he's here in the States. It's a brother. It's a black guy. It's a kid, like I don't know, 20s, whatever. But he built a plant that basically like a power plant, distillery or something that converts plastic back into gasoline. It's stuff like this. Like that's what we need to be working on, stuff like that. But again, we haven't got to that point where these people in power keep killing, keep assassinating and murdering our creators and our inventors, our healers like Dr. Sebi, all the people that are doing things that are constructive to actually help people. They you know wait and they connive and sit and try to figure out how can we get to them, and then they take them out. Bob Marley, like all these people that like were actually doing a lot of good. Nipsey Hussle, uh, they assassinate him. So it's like, you know, I low key am on that same tip. It's just I like, okay, we don't need any more martyrs. We need people that's like actually going to survive to help encourage as many people as possible. All right, so that's you know So anyway, it's just interesting things like that. So that's why we need as many people of light, many people as possible to like, because once you reach a certain threshold, then they can't stop it. All right. So anyway, interesting stuff. Interesting stuff. Okay. So the new engine's rate of emission is given by this function where EFT is the emissions in billions of pollution particles per year, particulates per year at time t in years. The emission rate of a conventional engine is given by this. Let me see, emission rate of a conventional engine is given by this, okay? So the graph of both curves is shown to the right. At what point in time will the emission rates be the same? Well, it looks like, what is that? It looks like when like x and t is 3. We can set the two rates equal to each other and solve. We should get, it looks like it's 3. And then what is the reduction in emission resulting from using the student's engine? So in other words, basically the area of the curve bound by the two regions. So basically, what's that point of intersection? So if we set them equal to each other, let me see if I can get back to my previous slide. Come on. Okay. I think I'm gonna just work here. I'm a little bit short on space. I could generate some space, but I kind of want to set these two equal to each other and solve. Let's just see what happens. So if we say what 2t squared equal to 9 plus t squared, we can, let's set it to 0, get everything to the left. So we'll have t squared minus 9 equals 0. So then what, plus or minus 3? So just the plus 3. Whatever the units for t is. Years, 3 years. So that's for part A. So that's, for looking at the graph, that's what we anticipated. We got 3 years. I'm gonna just put it like this. And then what is the reduction in emission resulting from using the Studis engine? I think that's it. Yeah, let's find the area under the curve. Okay. So that would be what the integral as x goes from 0 to 3. C of t minus E of t. So 9 plus t squared minus 2t squared dt. Okay, so I think we have some like terms. 1 minus 2 is going to be a -1. I'm going to make the change up here just because I'm short on space. So there should be a negative t squared. Okay. And then the integral is going to be what? 9t minus t cubed over 3. Did we just do this? Why does this feel the same? As t goes from 0 to 3. So when you plug in 3, we'll get 27 minus, is that 0? It looks like, wait a minute. 9 times 3 is 27 over 3 is a 9. Okay, we're good. So minus 9. So when we plug in 3, we got that result. When we plug in 0, we get 0. So then what is that, 18? What is the pollution particulates per year? Pollution particulates per year. Okay. All right, let's see how do we do. Let's see how do we do. You know, and there's still a lot of like inventions and things that there's still a lot of things that society needs. Like some of the stuff sounds alien, but it's like I don't even know. This was far fetched. I don't even begin to know how to do this. But they were like devices that can. Okay, now this is how you can be. It's a little bit more plausible. So the device that they were describing was something that like you can basically synthesize anything that you want. It can like reconstruct them at the molecular level and create whatever you want. That was the one that was far fetched. But in more recent, recent studies or experiments, scientists were able to like freeze light, right? And one of the narratives is that everything that we see is actually frozen light already. It's just being able to do it on command is a different thing. So that's one of the things that scientists supposedly have recently done as far as innovative ideas, right? So, because if you can freeze light, if you can turn light into, if you can slow it down or freeze it, then you can make matter, because that's essentially all the stuff that we see is frozen light anyway, right? But if you can take like a light and slow it down and do at the molecular, and at the molecular level, and change the structure or whatever, then you can essentially make whatever you want. Apparently, that's the theory. Another thing that is needed is like efficient batteries, right? Like imagine, you had a battery powered car or plane or whatever, and it only took like 5 minutes to charge, and it'll last you for X amount of years, right? Something like that, like or some other way to store the energy instead of like lithium. Maybe the minerals that they're using are not like they're rare, and so we need something that's more abundant, right? It's like, so the whole study of batteries, especially with everything becoming digital, like there's a lot of room for growth in that field of study, right? Okay, so let's see, how do we do, right? They're going to be the same when the efficient rate is equal to, what was that one, conventional, right? The conventional rate. So we got plus or minus 3. Again, -3 doesn't make sense in the context of the problem 3 years back, so we just take the positive, right? So the emission rates are going to be the same after 3 years. The reduction in emission is represented by the area between the graphs as t goes from 0 to 3. And I think we got 18 billion. The only thing we're missing was the billion pollution particulates per year, right? Billion pollution particulates per year. Right, that's the only thing we're missing was billion. But I think we got the 18. Matter of fact, I'm going to just go ahead and put right here, I'll just put a B for billion. Okay. All right. Let's see. What else do we got? Okay. That wasn't too terribly bad. We're about halfway. That's about right. Okay. So we have this definition. So let f be a continuous function over a closed interval AB. The average value, y average, over the closed interval AB is given by this. So 1 over b minus a times the interval as x goes from a to b of f of x dx. Okay. Average value, moving averages. Okay. So find the average value of this function over the closed interval from 1 to 2. Okay. So let's just try that formula that we had, right? The average value. So we'll say y average. Now the formula, let's go like this. One over b minus a times the integral as x goes from a to b of f of x dx. That's pretty much from the definition we just introduced. Okay, so let me see. We're going to be evaluating an integral as x goes from, it looks like 0 to 2. So that's going to be 1 over 2 minus 0. Okay, our f of x is x squared. We don't really need all that. So we say x squared dx. Okay. So then that's going to be half times, what is that, x cubed over 3, as x goes from 0 to 2. Okay. So that's going to be half, what is that, 8 over 3? And I think that's it, because when you plug in 0, it collapses. So then 4 over 3. Four thirds, 1 1/3, right? Yeah. And so that matches up with the graph, the average value. Okay. Okay. So Rico's speed in miles per hour, t minutes after entering the freeway, is given by this guy here. T is less than or equal to 30. I think that's 30 minutes. From 5 minutes after entering the freeway to 25 minutes, what was Rico's average speed? How far did he travel over that time interval? Okay, I think I'm going to give myself some space for this guy. This is slide 22. I'm glad I got that number. Let's copy. Here, I want to paste. Okay. And then from here, 5 to 25, and we want, how far did he travel? Let's see, what was his average speed? So we want the average speed, and then we want the total distance. Okay, we can get it. And like you know something's got to be up. Like when people that promote death and destruction get paid billions of dollars, you think that's accidental? Like, you know, they encourage them to promote self-destruction because they know that people are going to follow them as far as like shooting and all this other kind of stuff and drugs and all this stuff, because they want people, again, it's much easier to control someone that doesn't love themselves, right? You know, if somebody that is just self-destructive and destroying their community, destroying themselves, as much, then now you got an excuse to use the police. You know, it's on purpose. Like it's clearly on purpose, right? So anywho, okay, so we want his average speed, right? So let's see. So for part A, his average speed is going to be the integral as x goes from where, 5 to 25 of this function. Man, there's a lot going on here. I do not feel like doing this in the least. Okay, so minus 1 over 200 t cubed 3 over 20 t squared 3 over 8 t plus 60 dt. Oh, and then we need the b minus a, right? I was definitely forgetting that part. 1 over b minus a. So then 1 over 25 minus 5. Okay. So 1 over 20. Okay. That's going to be what? T to the 4 over 4. We got to keep that 1 over 200. Okay. Some multiplication in there. Plus 3 over 20 times t cubed over 3. At least we get some cancellation going on there. So that's going to cancel that. Three over 8 times t squared over 2. Okay. 60t. We want to evaluate this as t goes from 5 to 25. All right. Just trying to see if there's any more cancellation or simplification I can do. Okay, let's keep going. 1 over 20. So when t is 25, I don't know that one. Hey Google, never mind. Cancel. I got it right here. All right, so let's do 25 to the power of 4. We get that number. 800. Let's say divided by 800. That doesn't help us. Let me think. I'm gonna do some cancellation. So that's what? 25, 25, 25, 25. 100. So 2 times 4 times 100. So if we divide both of these by 25, this would become a 4, and this is gone. And that's about the best we can do there. Okay. So then the next one, I'm going to do this, 25, 25, 25 over 2 times 2 times 5. Okay, we can do it. So that would turn this into a 5. I think that's the best we can do there. Okay. This one is just more being tedious, all right? 625, nothing cancels there. I'm just gonna write it out. 3 times 25 times 25, 16, that's fine. 150 plus another 0. So 150 like this. So I'm gonna go like this. So this is the result when we plug in 25. We're gonna come back and keep working on it. And then we need to say minus when we plug in 5. So when we plug in 5, 5, 5. You know what? I'll just write it out. I'm just gonna put all this in the calculator. Like, I don't feel like doing this. 5 times 5 times 5 times 5 over 2 times 4 times 100. Okay, we'll come back to that. I need a negative in here. Plus 5 times 5 times 5 over 20. We can do some cancellations there. Minus 3 times 5 times 5 over 16. 30, so 300. And we want to evaluate this result as x goes from 5 to 20. No, we did that part already. We did that part. Okay. So I'm just gonna use my calculator. I'm gonna show some notes here, but I'm really just gonna use my calculator. Let me see. 5 times 5 is 25. So that would turn this into a 4, and that would get rid of these two. That would turn this into a 4. That would get rid of that one. And the rest of it persists. So I'm just gonna use my calculator, right? So the way I'm gonna do it, I mean, honestly, we could put the whole thing in our calculator instead of the individual parts. So for instance, let's just do the whole thing in the calculator just for the sake of simplicity. What's the time? So what I'll do, I'm going to go to my y equals, right? Because especially because we're evaluating, it should be okay. So I'll do my negative parentheses 1 over 200 close parentheses times x to the power of 3. Okay. plus 3 over 20 times x squared minus 3 over 8 times x plus 60. Okay, 60. Okay, let me check it one more time. 1 over 200 x cubed, 3 over 20 x squared minus 3 over 8x plus 60. Okay, so then from here, I think we go so to stat and calculate. No, that's not it. Let's go to math. There it is. Number 9, the interval number 9. So we want to take the integral of that function that we just inserted with respect to x, as x goes from 5 to 25. And we need to multiply that by 1 over 20. So I'm going to insert parentheses. We can do 1 over, it's a little bit extra, 25 minus 5. I missed my division symbol. Let's say times right here. I need to insert a division symbol. Okay. I think this will work. And it'll just spit out the final result for us instead of doing crunching all those numbers. Okay. So we got 68 3/4. Miles per hour. It's almost 70. I guess it's reasonable. So 68.75 miles per hour. Okay, that was his average speed from 5 to 25. Okay. And then how far did he travel over that time interval? So what's that time? What, 20 minutes? So that, if that's miles per hour for 20 minutes. Okay, let's do a conversion. Let me just do that real quick. Duplicate. And this one, I'm going to clear everything except the result. Okay, so say this is his average speed. Then distance should be, we got this 68.75 miles per hour. And here, let's do this. Miles per hour times, what, for 20 minutes? We got to get our units together, right? So we need to convert from minutes to hours, right? So we're going to say times 60 minutes goes with what? 1 hour. So that way, units of hours are gone, units of minutes are gone, and we're going to be left with our desired result of miles. Okay. So then we're going to say that answer times 20 divided by 60. So about 23 miles. So we'll say approximately, oh no, we do. $22.92 miles. Let's see, how do we do, right? So that's just kind of following the breadcrumbs. We kind of got to this conclusion. We're going to compare it to the prepared notes. Okay. Let's see, how do we do? All right. You done with me? Okay. There we go. Woohoo! 68 3/4, right? It was a pain. So, you know, they crunched the numbers. I mean, eventually, again, the challenge there was just being organized and keeping track of everything. I was like, forget about doing this by hand. As long as you understand the concept, you can crunch the number, right? We crunched the number. Now you can see how they did it. They got this astronomical number. Ultimately, they got to the same result that we got. All right, so which is fine. More than one way to get the job done, right? But we got, as long as we get to the same conclusion, you know, essentially for the most part, that's what matters. Okay. So then from there, so to find out how far he traveled over the time interval, we note that it's given in minutes. Yeah, I think we got that. They got the exact result, 22. Yeah, that's essentially what we got. All right. Third of an hour. Okay. All right. So we still got a good about 25 minutes. Let's keep going. Quick check. I think once I finish this, we might call it a day. I'm kind of. It just depends on the timing. Okay, let's keep going. So let F. Let me kind of check on you guys for a moment. Give me just a moment. So I don't see anything in the chat or the Q&A. So we're just going to keep rocking and rolling. Okay, so definition 2. So let F be a continuous function over a closed interval AB. The moving average function is given by this. Let me see. So I guess the average value was the y average. Moving average is f of the moving average of f of x. 1 over L times the integral as x goes from, or as t goes from x to x plus L, okay, of f of t dt, where L is a constant representing a fixed interval of time. Okay, so some fixed interval of time. Let's see this. So moving average. Okay, so the weekly revenue in thousands of dollars of trucks rentals X weeks since the start of the year is given by this, where X goes from 0 to 10. Find the moving average over 3-week intervals. So like basically the idea here is like we're gonna find the average the average value from the weeks from 0 to 3 weeks, right? We find that average value. Then we go back and we do it again. We find the average value from weeks 1 to 4. We do it there. Then we find the average value from 2 to 5. You're basically doing like 3 weeks intervals as you move along from 0 to 10, if that makes sense, right? So it's the same as like what we did a moment ago where we found the average value, but we keep shifting, doing it in intervals of 3 weeks. We do 0 to 3, 1 to 4, 2 to 5, 3 to 6, until you get to the end, right? And I don't think I'm going to write that out because it is a little bit verbose. I'm just going to kind of walk you through this. So our L is going to be 3 for every 3 weeks. To find a moving average for the first 3 weeks, we let X be 0, right? So the moving average of the revenue, again, our L is 3 because we're doing every 3 weeks. The integral as t goes from x to x plus L. So again, for the first set of 3 weeks, we're going to let X be 0. So then that's going to be as t goes from 0 to 3, right? You can see it there kind of on the right here. And I'm just not writing it because it's a repeat of what we had before and it's just like tedious. But if you understood the previous one, this one is essentially the same thing. You're just doing it in sets of 3, right? Okay, so the first one, again, as t goes from 0 to 3, and then it's just take the integral like before, right? So the hardest part here is getting to this point. Once you get here, then it's kind of a repeat of what we did before. Okay, so then you take the integral, right? You can even use a calculator. It's going to be the integral of all that. You get a result. So therefore, for the first 3 weeks, the trucks rentals had an average revenue of this per week. This is for the first 3 weeks. This is when we let X be 0. So now for the next set of moving average, you let X be 1. And it's going to give us the average value from weeks 1 to 4, right? You can see that here. And then it's a repeat, right? So here, let X be 1 between the weeks of 1 and 4. And then it's a repeat. So you still have your third, you have your 1 to 4, you take your integral, you're going to get something like this. So over these weeks, the trucks rentals had an average revenue of this per week. So then the next moving average is like you let X be 2. So that'll give us the moving average from weeks 2 to 5. You can see that here. So weeks 2 to 5, you get a result. Weeks 3 to 6, you get a result. Weeks 4 to 7. You see what I'm saying? Like we're supposed to be doing that And so this is where, like, if you had like a spreadsheet or your graphing calculator, where you would probably be using that to crunch these numbers. You really wouldn't do this one by hand. You could do it by hand, but that's excessive. This is something where you would use like TI-83 plus. I'm pretty sure you can do integration in like a spreadsheet, like numbers or Excel. And you have, if you have a Mac, I think Mac comes with a spreadsheet, with numbers. If you have Windows, being a student, as long as you have access to your Morehouse email, even after you graduate, as long as you can access your Morehouse email, then you have the Microsoft Suite. All right. I use stuff to this day because I try to keep my emails open, even from grad school and other schools. As long as your email is active, you can use a lot of their suites. Right? Till Kingdom Come, right? As long as you keep your email open and active, or as long as you're able to. Okay, weeks 4 to 7, 5 to 8, 6 to 9, 7 to 10. I think the 7 to 10 is the last one. So it was a total of 7 moving averages. All right. So moving average is again, once you get the average value, you get that concept. Moving average is the same thing, just how we did in this example, weeks 0 to 3 and then 1 to 4, right? It's the moving average, it's the average for those moving increments along a long time or whatever. Okay. I think that's enough. We still have about 15 minutes, give or take, but I think that's enough. Wait a minute. Let me at least glance at this one. So these are moving average. Yeah. So the graph below displays R along with the graph of the moving average over these 7 3-week periods of time. The graph of the moving average retains the general shape of the graph of R, but reduces the fluctuations, making the general trend easier to see. Okay. So it kind of matches the original, but removes a lot of the excessive fluctuation. Okay. The moving average smooths the data, but maintains this general trend.
Hey, Professor.
Yes. You have a question? Okay. Let me check the chat. Hang on. I see the message.
Hello.
Yeah. Go ahead. Is this Mr. Hodges? No. Anyway, I see Mr. Hodges mentioned. It's okay. Don't worry about it. Like, it's okay. Let me see. Okay. I think that's it. Let's do a summary. So the additive property of definite integrals states that the definite integral can be expressed as the sum of 2 or more other definite integrals. If f is continuous on a closed interval from a to c, and we choose a b such that b is strictly between a and c, then the integral from a to c is going to be the same as the integral from a to b plus the integral from b to c. That's fine. The area of a region bound by the graphs of 2 functions where f is greater than or equal to g over a closed interval is going to be the integral as x goes from a to b of f of x minus g of x dx. So we saw that one where we had 2 functions and we wanted the area of the region between the 2 functions. So integral is x goes from a to b of the upper function minus the lower function. All right, so that wasn't too bad. The average value of a continuous function over a closed interval, 1 over b minus a, as x goes times the integral of x goes from a to b of f of x dx. Moving average function is given by this. We might have some bonus lectures. It depends. I got to glance and see what's coming up, and I got to look at it. Because there are some other topics, but I don't think you're not necessarily responsible for it, but it would be great to kind of talk about it. Okay, anyway. It just depends on what's there. Okay, I think that's enough for one day. Let me see. So the only real announcement, again, if you like as far as my sports people, I see the emails, so just keep sending your schedule, and I try to update. I try to keep an eye out for my sports people. But yeah, if you feel like you might be in that list, or if you receive the email about purging, or if you feel like you have like 4 more unexcused absences, just send me an email saying, hey, I think I might be in that category of excessive unexcused absences. I do intend to finish. Please do not purge. Because I'm going to go back and kind of go through my records on Thursday to update this and submit names. Now, they may or may not purge, but if you, again, just try to stay off of that list, just reach out to me. Send me an email and text me. Text me is the best. Email is for records, right? So you email me just to have it on file, and then you text me to get my attention. Because once I leave you guys, I'm off running around. Just just running around, really. Okay. Are there any burning questions before we go our separate ways? I saw the thing in the chat. Don't worry about that. If there aren't any burning questions, then we'll end the session here. Yes, go ahead.
Professor.
Yes.
Can I go ahead and take exam 2 and not have to wait for it, or I have to wait for it?
You should wait. It'll be out soon, especially since we're approaching the end of chapter 4. Yeah, just wait for it.
Okay.
All right. Any other burning questions? Going once, going twice. All right, gentlemen. If there are any other burning questions, we're going to go ahead and end the session here. We did 4-4 today, so on Wednesday, you can anticipate 4-5. I think that you're only responsible for 4-6. I might cover 4-7 or 4-8, but I won't make you responsible for it. Whatever's on my math lab, that's essentially what you're responsible for. Again, if there aren't any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy your evening. And we'll meet back on Wednesday, same time, same place for the next installment. All right, gentlemen, take care. Peace. All right, let's go here. Like I said, let's go ahead and do my attendance. I think I'm going to do it here. Let's chat. That's okay. Okay. It's fine. Let me screenshot this.